There we go. You got it. Multinomial. What if you have a 3-category outcome? What if you have a Republican, Democrat, and Independent? You want to predict. Or leadership, authoritarian versus permissive versus laissez-faire. So now you can move into multinomial logistic regression. So let's just say I made up some data. Let's say I have leader type. And the option, everybody, the option in SPSS is analyze, regression, multinomial logistic. So there you see multinomial logistic, which has a similar interface to binary. So this is if you have 3 or more outcomes. And you see here, authoritarian, permissive, transformational, and I'm going to have self-educate, predict. If you self-educate yourself, what's the probability you'll be one of those types of leaders? So this is obviously fictitious data, very small sample size, but I just want to show you this as a statistical option. You do get the intercept-only model, which you recall from binary logistic equates to step 0, and then the final model. So you see the chi-square went from 37 to 27, the chi-square is 10, the p is 0.035. So that tells me so far for the full model that it seems the model improved by adding the predictor. And you get, see here it actually calls them pseudo R-squares. And here you get the likelihood ratio test. A likelihood ratio, again, is basically the full model over the most restricted model. It's a ratio of models. And here we actually see we have significance for age, but we do not for self-education and predicting type of leadership. So there we get an idea that, okay, overall, the model fits. It's significant. We see overall age is significant. And then you get the parameter estimates. This gets a little more complex, everybody, for multinomial, because it essentially dummy codes the DV. It dummy codes the IV, but do you see what I just said? It dummy codes the DV. So you have the full solution for the authoritarian group. You have the full solution for the permissive group. But you don't see anything for laissez-faire, right? Or let's say I called it transformational. Right there, the reference category is transformational. So this is authoritarian versus transformational. This is permissive versus transformational. So when people have gone on the net saying, they go, what if I want to compare authoritarian versus permissive? Guess what we have to tell them to do? You have to recode the DV. There's no way. You can do it by hand, but you've got to recode the DV. So here I can get predicted probabilities. They're going to be managed out for each of these groups. And that's called multinomial logistic regression. That's multinomial logistic regression. Just so you're kind of aware of it. Any questions on that? So I just want to give you the ballpark. I haven't used it too frequently. Probably the most extensive use of it was when I was consulting with the University of Arizona on a study that got funded by the National Institute of Drug Abuse. And I brought this up in 6022 when their DV was 5 different types of cigars, because one little epidemic they're finding is from the 18 to 22 years old, they're smoking these type of cigars. I forget the name, like Becker, or I forget the name. There's like they're flavored cigars, and they're inhaling them. And they've got, she said, they're like 20 or 30 times the toxicity of cigarettes. Have you heard about that? Little cigars, they're like flavored cigars. You've heard of those? Yes, that was something. I remember that. That was one of them. And I guess people are inhaling them, which is she said, what's that? She didn't use that word. She said toxic. And so we actually did a multinomial logistic looking at predictors of which of these type of cigars. I remember one was particularly popular. I forget which one, but there was one of those 5 that really had a lot of use. So that's multinomial logistic. So if you ever have 3 different types of leadership as an outcome, you could use that statistic. Now what if you have a count outcome? And again, this is all from 602.2. You won't have to do this for your take-home, only binary logistic. But I want you to know about these. What if you have a variable that's a count? Violations, relapses, length of stay, Number of absences in the past year. Number of times you've been scolded by your supervisor. Right? Number of, etc. All these variables technically are what's called a count. What is a count? Literally counting 0, 1, 2 within a circumscribed time period. So there's this thing called the Poisson Distribution, and the Poisson Distribution has to do with a count within a certain time. Here the mathematics are a little bit different. The probability that you can have 1 absence, 2 absence, 3 absence is the probability of y given the mean. So let's say that Stacy knows that the average person has maybe, 0.069 absences a year, right, for maybe archival data or something like that. Then you exponentiate the mean, right, exponentiate minus the mean, 0.069, by the mean, 0.069, to the number of occurrences. What's the probability? Given that the mean person has 0.069 absences a year, and Zach's got 3 absences. He's got 3 this year. Do you see this thing called y? Y factorial? Do you remember what factorials are? 3 times 2 times 1. Exactly. That's how you get the probability for a Poisson process. So what if I ask you number of times you've relapsed? Let's say I'm going to do a study on alcohol relapse. Here we see 6 people have 0 relapses. 5 have 1. 4 have 2. 2 have 4. Does everybody see that? And the mean relapse is 1.5. So if y equals 0 relapse, and let's say the mean is 0.3. Let's say we know that the mean is, there's one thing, but it's 0.3. We can go ahead and put in the equation and say 74% probability of 0 relapses. So, this assumes what's called equal exposure. It means that each unit, which would be a person, has equal opportunity for occurrence of DV. Each person has an equal occurrence of 0 relapse, 1. If you think they're unequal exposures, because maybe ethnic makeup, maybe geographical, is there a chance that maybe certain geographical locations might be more susceptible to tuberculosis? I think there are some areas. Didn't they get some TB breakouts lately? A few weeks ago, I think LA had some. So those are things that if you think that there's differential exposure, especially in epidemiology, they make sure to account for that in their model. For now, we're going to assume equal exposure. There used to not be a way of doing Poisson modeling in SPSS. There was a macro someone had developed and a way to work around it. But now there is, everybody. You wouldn't know it if you went to analyze regression. It wouldn't be there. So you'd be really confused where Poisson is. If you looked, you wouldn't see that option. But if you go to generalized linear models, and under response, I'm going to type a model, hit a thing called Poisson. There it is. See where it says count? Poisson log linear. Why is this a generalized linear model? Because we're using the log as the link function of the outcome and the probability and the predictor. So you get very similar, everybody, an intercept model with no predictors. And look at the link function, the log link function. And look, initially the DV has a mean of 1.5 relapses, which we already know. And you get this goodness of fit output. You get the deviance, which is a kind of a residual, the chi-square, which is model fit. Then you get all these information theoretic indices. What those are used for is they kind of say, if I want to compare models, which one is better. You're going to find when you get into structure equation modeling, you get either the AIC or the Bayesian information criterion. The lower the number compared to another model, the better. So Ross decides to add age, a number of years on the job, and you can see if this goes down relatively to see if there's model improvement. Here's the test of the full model. It is significant for the intercept only model, 0.026. See, it's only the intercept. No predictors. No predictors at all. And note, everybody, if I exponentiate 0.405, Guess what it equals? For the intercept model only, 1.5, which is the mean. Which is the mean. And if you want to, you can add predictors. Right? I'm just showing you basically the Poisson. Of course, at this step, you would start adding predictors. So the Poisson model is appropriate when you have a count outcome. And I've seen some people here do analysis when they really should have used a Poisson model. But they didn't know how to analyze it. They didn't know about it. They have what looks like a normal distribution, and they use regression. But if it's truly a count variable, if it's number of absences, number of people, number of times turnover, anything that's a count, you should strongly consider a Poisson model. I've used it quite a bit in literature, and we even co-authored an article with UCSD Med School using Poisson modeling. And just so you know, everybody, there are many other options here. There are many other options with generalized linear models. Just so you know, negative binomial. One of the assumptions with Poisson models is the mean equals the variance. It's this weird assumption that the mean equals the variance. If there's a higher variance, then you may want to use a negative binomial model. Then there's ordinal regression. If you have an ordinal outcome, we discussed this briefly already. And here you have the ordinal logistic or ordinal probit. The logistic uses the EX as the link function. The probit uses the normal distribution for the errors. And then binary logistic, binary probit. Binary probit, which we haven't gotten to this class, is very similar, but can be used in lieu of logistic. The probit uses kind of a similar S-curve, cumulative distribution function, but assumes the errors are normally distributed, follow a normal distribution instead of the logistic curve. So there are, just so you know, a lot of options, everybody, given the type of outcome for these regression models. So that, everybody, is kind of the binary logistic, multinomial logistic, and Poisson modeling. You're mainly going to be doing binary logistic for your take-home. You're going to be mainly doing that. Let's segue now into log linear modeling. And there is a chapter in your book on log linear modeling. And I'm not going to go deep into this. You will not have to do this for your take-home. I don't see many people doing log linear modeling. It starts with the chi-square. It's actually it's a great chapter on this. Log linear modeling. What if you have a 2 by 2 by 2? What if you have a 2 by 2 by 2 and you technically for now don't have a DV? You just want to see an extension of the chi-square. So what if you have something like this? What if you want to look at the relationship? God, this is almost going out here. What if you want to look at male, female, okay, male and female, and let me see how I can split this up. Male, female, and then I want to look at executives versus staff. Executives versus staff. So does everybody see, so far this would be a 2 by 2, right? Sex by clerical. And then let's say, okay, then let's do, here we go. Profit, not for profit. Profit, not for profit. Male, female, executive versus staff. Does everybody see this is a 2 by 2 by 2? Can't just do a chi-square because you're restricted to 2 variables. This is when the flexibility of log linear modeling comes into play. And it's based in part on what's called the multinomial distribution. And we already got exposed to that a little bit with multinomial regression. It's basically an extension of the binomial distribution. What is the simplest way to show a binomial distribution, or at least the mathematics on it, is if you have N and R. let's say n, let's say you have 300 people and 189 pass, let's say 300 people take the bar in San Diego for the law degree, and not law degree, but lawyer, and 189 pass it, right? 189 pass it. Or let's make my math a little bit easier. Let's say 66% pass the bar. So the probability of n times q, n minus r, is the binomial distribution. In other words, I can go ahead, the probability, 60% of people passed, right? Does everybody see 60%, 66%? 0.66 raised to the power of 200. 0.33 or 0.34 did not pass. 300 minus 200 would be 100. Did not pass. That's the binomial distribution. That captures the binomial distribution. Bless you.
Thank you.
So there you go, everybody. You get a probability associated with each of those. And that's the binomial distribution, which was used a lot when you flip a coin. When you flip a coin, think about it this way. Probability of getting heads is 0.5. Let's say you do 40 flips. That'd be 20. Probability of getting tails. There you go. And what's kind of cool about the binomial distribution, especially with enough trials or events, it can be a normal distribution. It can be a very close cousin to the z. It assumes, yeah, there's independence. It assumes there's independence. And you can kind of see, similar to what I just did, one other way of calculating this is looking at the factorials. So if I got 20 successes or 20 flips of how many, you can actually get the same results and get a probability associated with each of these possible combinations. So that's the binomial distribution. That's for a simple dichotomous event, live or die. But for multinomial, what if you add a third variable? What if you add a third variable to the mix? Then you get into this whole area of what's called log linear analysis. And there's the log linear, everybody. And there's a few options: general, logit, and model selection. Remember, the logit is the log of the odds. The logit's an interesting animal. So you're going to see that's when you have a true TV. So for now, let's look at status, self-education, and sex. Status is being managed out versus not managed out. Self-educated, yes or no. Sex, male or female. So I'm going to keep this simple. 2 by 2 by 2. And if that's the case, you will want to look into log linear modeling, everybody. Initially, this is what's called a saturated model. What is a saturated model? How many degrees of freedom do you see? 0. Because look at it, everybody. If you have a three-way interaction, how many tests of effects do I have? If I have a three-way interaction, how many tests of effects do I have? Does anyone remember? Anyone? 7. Why is it 7? Anybody? Variable 1, variable 2, variable 3. Variable 1 times variable 2, variable 1 times 3, and 2 times 3, and guess what number 7 is? The three-way. So it gets busy, doesn't it? Well, if you start having to estimate all these parameters, each time you estimate a parameter in statistical modeling, you lose a degree of freedom. You lose a degree of freedom. So it's that much more that needs to be estimated. Which is why this can get, I remember the first time I was asked in one psychometric class years ago, many years ago, before I understood log linear modeling, they said, Dale, would you give a lecture on log linear modeling? I knew this much about it. I was never taught it in school. And I remember presenting things like this, saying, wow, value of 0.0, no p-value, it's a really good model. Well, no, it's, because I didn't know what the hell I was saying. No, it's a saturated model. It's a saturated, and that's why sometimes in path analysis, this can really confuse students when they run path analysis. And if they start having as many paths as there are elements in the variance covariance matrix, they get a degree of freedom of 0, they get a chi-square of 0, and they get a p-value of 1.0, which is good. They say, guess what? I got perfect fit. Well, you have no degrees of freedom. You have nothing to disconfirm. So this is the busiest model. Usually you're going to want to constrain it. But what is helpful with a saturated model is you get parameter estimates. You get parameter estimates. And remember, you just told me there are going to be 7 effects, or I kind of told you. 1, 2, 3, 4, 5, 6, 7. It's kind of like having a bunch of dummy codes, isn't it? So we were discussing a little bit, right? See, and this is just for a 2 by 2 by 2. You were talking about a 4 by 7 by 2. So here, I got 7 effects for the simplest model. For your model, if you wanted to dummy code everything, you've got a lot.
Yeah.
You got a lot. And then you got to interpret it, Chad. Each one. So here you can see which ones are significant. None of them are significant, but I'm doing this more for illustration. But I get kind of the individual effects of status, self-education. This is like, it's kind of like logistic regression. Really, these are kind of like logistic types of values, probabilities. None of them are significant. But that's log linear analysis. And look what the default model is, Poisson. The model, actually that's the default, that's the link function that uses what's called a logarithmic link function, hence the term log linear. It literally converts every single number in the matrix to a logarithm. However, that's a busy model. So what if Zach says, well, you know what, I think I'm going to restrict my model and I'm only interested in education time status. Let's say Zach says, I'm not interested in the other 2 ways, I'm not interested in the 3-way, but I am interested in the individual predictors. Now Zach gets a goodness of fit test. Now because you have degrees of freedom. You have room to move. And we see the likelihood ratio is not, this is tricky. Likelihood ratio is not significant. The Pearson chi-square, is and isn't. You don't want significant for goodness of fit, because you want the model to fit the data. This would be a tough one to decide which one to use, because one is significant, one isn't. And you get a much more restricted model. Because now you're only, because of Zach's model, right? I don't have all the 2 ways, I have just one 2-way. And we see here's the test of significance for status, for self-education, for sex, none of which are significant, and status by self-education. So Zach's 2-way interaction is not significant. You do get a 95% confidence interval, and this is a confidence interval around the estimate. So that, everybody, is one approach to log linear modeling. Now, there is another option using the model selection option. So using model selection for log linear analysis. This one's a little bit different. Here, what can be a little confusing, you get a test of K-way and higher order effects than K-way. So in other words, there's 3 main effects, right? There's 3 main effects, 3 2-way interactions, and 1 3-way interaction. And we can see here, even though it's hard to tell, but I can tell by degrees of freedom, we can see the 2 ways are significant. The main effects and then the 3-way, because there's your 1 3-way. And we see it is significant for the 2 ways. And however we order it, we see that, you know what, maybe there's something going on with the 2-way interactions. The 3-way is not. So you may want to reevaluate your model and get rid of that 3-way. So you may want to consider the 2-way model only. Possibly. And we do have 1 significant 2-way, self-education by sex. So then you can start maybe doing some bar charts. Right? Maybe do some bar charts and see what it looks like. So, maybe just do a quick little chart like this to have your audience understand what the heck is going on. So if you're male, you tend to self-educate. Females, not as much. There you go. That would show the relationship for the log linear analysis. And I always provide these types of graphics because people can get just overwhelmed with the percentages and so forth. And then you get the summary. There you get the summary of each of the models, self-education sex, and we see that it is significant, 0.006. So that, everybody, is just a preliminary exposure to log linear analysis when you have categorical variables and you're looking at the relationship if you have 3 or more. What would some people do? What if they know nothing about log linear? What if they say, man, this is way over my head, this is too complex, I don't get it? Then, what you may want to consider, everybody, so if you have 2 by 2, male, female, Republican, Democrat, and you really don't want to do this stuff, you could do 2 separate 2 by 2s. You could do one for profit companies, one for not-for-profit. But are you examining a 3-way interaction? If I do 2 separate chi-squares, am I addressing the interaction if you work for profit, not-for-profit? Right? So in other words, what I've seen some people do is analyze, they go into chi-square, status, self-education, and then under layer, right, they maybe hit on sex, put sex right there, and they do male, female, they get separate chi-squares, right? They get separate chi-squares. But is that addressing a 3-way interaction? It's not the same. And I've seen some people kind of address it as if it is. The way to get the 3-way is to do the log linear analysis. Now what if you truly have a DV? What if you have a dependent variable? Then you can do, the last option log linear is called logit. Then there is a logit option, everybody. So what I've shown you so far in log linear, I've shown you the general, the model selection, and the logit. Here, you truly have a dependent variable. The other ones, you're just looking at the relationship of these somewhat exogenous variables. Here, you really do have a dependent. You do have a dependent. So let's make status managed out as a dependent. Self-education by sex. Here you get the model. Then you get a real different statistics. Things like concentration and entropy. Entropy in physics, I think, has to do with chaotic systems, so to speak. This has to do with actually variance or dispersion. Apparently with entropy, the higher the better, from what I've read. Here, a design matrix shows you exactly what's being estimated. A design matrix usually has a bunch of 1s and 0s. So it's showing you it's going to go ahead and have, here's for sex and self-education. It's going to look at it for stay managed out, but everything else gets a 0, because it's like dummy coding. So this kind of gives you an idea of everything that's going to be estimated. And there's your parameter estimates, everybody, when you have a DV. So there you see we have the constant, and you have status, 1.6, and we can get an idea to see what's significant for each of the main effects and the interaction. And here, you truly have a DV, but it uses a log linear type of modeling. Where does it get complex? If you try to slip in a continuous variable, you're not going to like it, because it's going to treat it categorically. It's going to treat it categorically. If all of a sudden you do something like this, if you do analyze, log linear, logit, and put status there, put self-education there, sex there, and then age there. It's a little busy, isn't it? And that's only row 1 of row 100 of 112, right? Because age is a continuous variable. So sometimes people really are having troubles grasping this, and they use a logit analysis for this, and they put a categorical variable. That's a problem. One option with these logit models, if you want to put it in a continuous variable, is, and be clear on this, everybody, be really clear on the logit. Sometimes you will have this option. See, if I try to put age in, it's not going to let me. So what if you have a continuous variable, everybody? If you have a continuous variable and a categorical for a logit model, categorical, then I would just do binary logistic or multinomial. There's no reason not to. No reason not to. I do want you to make the distinction also, everybody. When you get into some of these more sophisticated models, such as generalized linear models, be clear on when you see factor versus covariate. A factor is a categorical variable. It's categorical. A covariate is continuous. In other words, they're all covariates. Technically speaking, they're all covariates. But this is if you have sex or age. Sex or leader type. Here, under covariates, when you put continuous. And you'll see if you put it in the wrong box. Because you're going to get, if you put age here, you're going to get every single combination of the age from 20 to 80 years old. So you do need to be clear when you get into more sophisticated modeling. So that, everybody, is kind of the ballpark lecture on log linear modeling. So log linear modeling is when you have really 3 or more categorical variables in which you can go ahead and have the structure of it be as complex as you want. And look at the relation between sex, by ethnicity or so, and what I had wrote there, maybe profit, not for profit. And that's log linear modeling. You can use the logit option when you truly have a dependent variable. When you have a dependent variable. Now, just so you can see, I've already briefly introduced you to generalized linear models. And what's nice with generalized linear models, they are able to adapt to binary outcomes. You have binary outcomes right there, binary logistic, binary probit, ordinal. If you have a count variable, very flexible to use generalized linear modeling. The other advantage of generalized linear modeling is the option to put in fixed factors, categorical and continuous, and to model all the possible interactions. So when you put in your model, it gives you the main effects and interaction option. So it's very, very, very flexible in that way. Also, one other thing I wanted to show you. I wanted to also show you another option here, which is closely related. It's called generalized estimating equations. Generalized estimating equations can be used also if you have a dichotomous outcome. Let's say you have, try to think of a dichotomous outcome. Well, let's take a clustered example. Let's say you have 30 people from human resource, 40 from finance, 30 from marketing. So let's say you have 29 different departments at Qualcomm with sample sizes ranging from 30 to 80. Nice sample size. You could just analyze it as one big database, right? But there's a little problem there. Possible violation of independence. You got cluster effects. Is there a possibility that people within HR, people within marketing, they share certain sentiments? They have certain commonalities. They have the same types of training. Which means you have to defend yourself in the name of sampling that there's complete independence, which is going to be a really hard argument to make. So if you inherit some huge database with 10,000 people from some organization, and there's 28 different organizations, 40 different departments, I'm going to come at you and say, how are you accounting for the violation of independence and or clustering effect? Because there's going to be clustering. Which means there's a whole suite of statistics, including multi-level modeling, and, which we'll discuss later, but generalized estimating equations to handle clustering, to handle that type of clustering. And, which means you have this thing called a subject variable, which might be department. Right? Let's say you have 29 different departments. So the variable is called department, D-E-P-T. You put it in there, and it takes into account the clustering. And what's really cool about this, everybody, is you have incredible flexibility for the correlation matrix. And we're going to talk briefly about this autoregressive, unstructured, of the variance covariance matrix. And you can have, what if you have a dichotomous outcome? What if you were looking at turnover? Yes or no? What if that's your DV? And you have a clustering effect. You can't just do your little logistic regression, because they're not taking into account clustering. So you still have the binary logistic option. You have your binary logistic option. So the generalized estimate equation can be used, A, for any clustering effects. Very, very, very helpful in that regard. Also, a lot of people use it when you have repeated measures. What if you have repeated measures? What if you sampled your 10,000 employees on a monthly basis over 3 years on job satisfaction? You got 36 potential data points for each person. You're not going to do repeated measures for that in ANOVA. There's going to be way too many parameters to estimate. Generalized estimate equations, similar to multi-level modeling, is equipped to handle not only these pretty time-intensive studies, but also, what if Chad answers 28 of these, Stacy answers 15, Ross does all 36? It can be really flexible in how to accommodate these type of structures. So generalized estimating equations, and what's really cool is, what if it's an ordinal outcome? What if it's a one-item job satisfaction? I enjoy my job. Strongly disagree to strongly agree. You can't just pretend it's continuous for an outcome. Then you have these ordinal options. So these models, generalized linear modeling, generalized estimating equations, are further extensions of logistic regression and so forth, but incredibly flexible. And generalized estimating equations can also handle time-based studies. The data entry is really, really different, everybody. It's really different. And I know I've shown this to you before, but well, let me just show you over here. So let's say I have ID, DV, repeated measures, you're used to the multivariate display. Time 1, time 2. Here, look at it. Here's Zach, 3 measures over time. There's Stacy, 3 measures. There's Chad, who took it on a couple extra occasions. Really flexible. And this is the data structure for multi-level modeling also. So here you can see, instead of it being repeated measures, it's got this type of display. And that's how you do the data entry, because what will happen is you'll go into generalized estimating equations, and then under subject variable, you'll put ID right there. And then your response variable would be your DV there. And this is, it asked me, are you sure you only went an intercept-only model? And I said yes, because I had no predictors. And there, look, it already tells me, everybody. It tells me, oh, look, you have 3 people with a minimum of 3 measures over time, and there's Chad with 7. See how incredible it is? Because if this was repeated measures, guess how many it would get rid of who? It might get rid of Chad, or if there was missing data. Let's say it wanted 7 for everybody. It's going to only have Chad to analyze. And you can get a predictive equation, everybody, and a model fit. So generally, and it takes into account clustering, the non-independence. So again, I would highly encourage you to examine and consider these tools as you run to these more complex, especially more and more of you are getting archival data sets for your dissertations. You're not collecting your own data. You're just getting them from wherever. So you get your data with 12,000 people from CCL, and I'm going to ask you, how many organizations are there? Oh, 27. Really? And are there any departments? Yep. Can you assure me there's a complete independence of response? No. Do you think there might be some cluster effects? Yes. Well, then you can't use your good old ANOVAs or regression. You need to take into account those very different types of sampling type of strategies. And now we have the tools. In the old days, SPSS didn't have it. Now they've got it, so you can virtually point and click away at it. It used to be pretty difficult to fit these models. Now it's definitely easier. So that, everybody, actually shows you a lot. We start with binary logistic. You now know about multinomial, ordinals, if you have an ordinal outcome. Probit is a close cousin to logistic with normally distributed errors. And now you also know a little bit about log linear modeling. When you have categorical variables, you want to see the relationship up for 3 or more variables. And a logit, when you have a dichotomous or a categorical DV. And that, everybody, and just to show you very briefly, what if you have an ordinal outcome? What if you have an ordinal outcome. And I know I showed this to you in 6022, but for now, let's just pretend number of relapses as opposed to a count is ordinal, which some people do. Some people would say instead of being a count, they'll say it's just ordinal. And then let's have self-education as a factor and age as a covariant. Again, everybody, this is where you can make a huge mistake. A factor is categorical, a covariant is continuous. It's continuous. We'll keep this, let's add, I don't want to scale models, continue. Location, main effects model, options, looks good. Output. We'll get some of this stuff here. And there you go, everybody. Here we have number of relapses, 0 relapses, 1 relapse, 2, 3, 4. Technically, it's a count variable. But let's just pretend it's ordinal. Let's pretend it's a 0 to 4 point self-report scale, which many of you will probably say, I'm just going to do a regression. But if you decide to add one item, that's job satisfaction, you really should look at an ordinal regression. And you can get a test of your model of which we don't want significance. I'm sorry, for this one we want significance because it's the model fit. Oops, it's not. Pseudo R squares, they're almost 0. The parameter estimates gets a little tricky. Here we see location, we see age is not significant, nor is self-education. Then you get these things called thresholds. And what the heck is a threshold? Actually, I've introduced this to you last semester, but just so you know, when you have ordinal outcomes, everybody, when you have ordinal outcomes, let's have this be infinity to negative infinity. Threshold 1, threshold 2, threshold 3. Let's say it's a 4-point response on healthcare. Poor, fair, good, excellent. Can I get a certain percent of people up to poor? Right? We got poor. No, that's right. Poor, fair. Because this is running out, I need a new one. Poor, fair, good, excellent. Do I have a certain percentage of people that are poor? A certain percentage of people that are fair? A certain percentage up to good, and then excellent. So it's called a cumulative logit model. Cumulative logit, or in medicine, they call it proportional odds modeling. There's actually a term called proportional odds. And then these actually become type of z-scores associated with, if there's 20% that are poor, you can get a z-score. 60% up to fair, you get a z-score. And that's why you get, with ordinal models, threshold. Basically, how ordinal models are analyzed in these sophisticated models is we assume, even though you've decided to measure this as an ordinal item, there's an underlying normal distribution. In other words, y kind of approximates this y asterisk, which means this is the kissing cousin of which correlation? Point biserial or biserial? Does anyone remember the difference of point biserial versus biserial from 6022? You just had it.
Wasn't it like categorical, like real categorical?
Yes, which one is the real one?
Point biserial.
Real, it's a categorical and a continuous, and a biserial is a continuous and a...
Is the categorical, but it's not, it's like a false
artificial dichotomy.
Yeah.
You got it. So, the biserial actually does stuff like this. It assumes when I answer, are you more nervous about your security after Boston? Yes and no. Let's say it's a survey. Is there probably an underlying distribution of how people are nervous about maybe being in large crowds after Boston? Even though I may just have the survey be yes or no. So that's why it kind of converts some of these things to probabilities and z-scores and starts to almost pretend there's a normal distribution even under yes or no, right? Some things are truly dichotomous. An item is true or false. But if I say, generally, do you feel sad? Yes or no? Could there be kind of an underlying distribution? And that's why with ordinal models, you get these types of things called threshold parameters. Very, very different type of statistic. I was talking with Chad about when you have categorical variables, sometimes the correlation matrices are very different. Technically, you get into what's called polychoric and polyserial correlations with these types of models. So that, everybody, is also if you have ordinal models. So now you know you have this kind of whole suite of statistics that you need to be mindful of, and means that you do not default to multiple regression. Assume, even if the residuals are normally distributed, if it's a count variable, it should be Poisson. If it's ordinal, you should use these proportional odds model. Another thing why we use binary logistic regression, because some people have said, if I have a 0-1 outcome, what's the harm of doing multiple regression? What's the harm of using the identity function, which minimizes the residuals? What's the predicted probability that can range? What's the range of a predicted probability for heart failure? From what to what? What's the predicted probability? What's the lowest it can be, and what's the highest? 0 to? You can get stuff like -0.3 as predicted probabilities. 1.45 as a predicted probability if you use regression. Also, do you think when you have logistic models, let's go ahead and do a regression. Linear, status will be the DV, self-education in the IV. Let's go ahead and look at Z residuals there, Z predicted there. Now the residuals may be normally distributed. Because, right, you may have a range of probability. How's that heteroscedasticity looking? It's not going to be homoscedastic, is it, when you have a binary outcome? Do you see why? You got people that either were managed out or not. In other words, you're not going to have homoscedasticity of the residuals if you use the identity link function for a binary outcome. The residuals may look okay, but there's no way you're meeting that assumption. Plus, you get probabilities that don't make sense. You make it. Let's even see if we get some weird stuff here with regression. Regression, linear, save. Let's look at the unstandardized and standardized residuals and the predicted scores. Okay, so the predicted scores. Let me go ahead here. Oh, you know what it is? If I have a binary predictor, it'll be the same. It's when you have continuous that you're going to get predicted scores that are really screwy, even those that are negative. So that's why, everybody, we will go ahead and use good old regression, binary logistic. That, everybody, is everything up to that point. Let me briefly go over the take-home and start with a brief review as we get the path analysis. Just for your take-home, everybody, which will be due 600 weeks from now, right? What did I say because of Zach? We're giving you, what's that?
3 weeks, right?
3 weeks. No ifs, ands, buts. You got to have a hard copy, everybody.
Yeah.
And I've got the database. I got everything appended there already. Take home number 2. Again, 3 little questions. See? 3 little ones, Chad.
Multiple choice. A, B, or C.
You can go ahead and put that down if you like. Here, it's going to be your homeworks, pretty much. Just that's why your homework or practice. You're going to use the same data set. Here's the group. The first one, you'll find 12 items that are used to measure the umbrella, construct, and quality of life. Database helps because the names are kind of already given away in the label, so you don't have to sit there from scratch and figure out what it is. But I want you to do an EFA. Remember, as opposed to the homework, I don't have a problem with you playing around with 2 or 3 or 4 factor solutions. But show me what the unrestricted one is first, right? Show me the full one. Then, if you want to play around, which you almost all of you did, that'll be great. And then I ask you, you'll find 12 items about quality of life. To assess the stability, I want you to use 2 rotations, Varimax and Oplement, and the extractions. I don't need all 4 extractions. So sometimes you can kind of maybe put them in a nice Excel table if you want. But I don't need pages and pages of output. Provide a comprehensive summary, communalities, rotating solution, eigenvalues, and results that may be a bit different than you anticipated, right, if it doesn't go the way you thought. Do you think there could be a linkage of the provision of a corporate-sponsored wellness program and one's quality of life? You know, give me an argument. You don't need research. I just want you to give me an idea. You're interested in comparing the 2 groups on these two psychosocial outcomes, psychological health, social support, same as your other homework, everybody. We're going to have a covariate of age, and there is one missing value for age. So don't worry about doing missing data imputation. We're just going to go with it. So I'm going to go ahead, you're going to hold age constant, same as the other homework. You're going to test the assumption of homogeneity regression. You're going to look at the correlation of covariate outcomes. You're going to look at the linearity, look at all the assumptions, the Romanova and Mankova, and see if we gain some strength with the covariate. As a finale, I'm interested in exploring which of the outcomes best separate the grouping variable. So the treatment will now be the DV. Hence, the first part is to conduct discriminant analysis using all these scales. You're going to discuss and summarize the DA analysis and the results of both description and prediction. Discuss the assumptions, which is boxes M. Further, run this with the jackknife procedure and see if the classification varies. Then, as we lectured today, I want you to compare it to logistic regression. It's kind of like you're doing your own little Monte Carlo study. So I want you to see if they're similar. Does one variable that's significant in DA, significant in logistic? Run the same model, interpret the logistic output, look at the odds ratio, probabilities, sensitivity, specificity, the Hosmer-Lemischow test fit, compare the origin-only model. Also, I've recorded the treatment group variable so that 0 is the control group and 1 is the experimental, as that make interpretation logit a bit easier. In your opinion, is there much symmetry between the results for the two techniques? Indicate where they converge and or diverge. So this will be kind of your own cool little example of seeing if the parametric versus more non-parametric technique, if they pretty much give you the same type of results. So that, everybody, is your take-home due in 3 weeks. Okay? Questions? Okay, let's start within this remaining time. We're going to do an intro on path analysis and structure equation modeling. So we're right on schedule. Ross, come here, please.
Yes.
Unfortunately, this doesn't work very well, but you'll be fine. Job satisfaction, you can just call it JS because it's kind of running out. Organization involvement, how involved you are, we'll call that OI. And then job stress, we'll call that JSTR. Tell me which one you think causes which one causes which one. Tell the class, give them your interpretation.
Stress affects job stat, which affects organization.
Okay, tell the class why.
Well, I guess the stress is a quadratic type of equation, but the higher stress you get, I think, and it's very low stress, you'll have lower job stat as well. And then the higher your job satisfaction, the more involved you're likely to be.
You're more involved? Okay. Okay. And do you think their stress also impacts involvement?
Yeah. Same way.
Okay. Good. Please, have a seat.
Lots of pleasure.
Chad, come here. Give me an alternative model. Give me an alternative. Same variables. And now give me an alternative using the same exact variables, but an alternative model from Ross's.
Okay. Well, let's say that the more involved I am in my organization,
Okay.
the higher my satisfaction will be, so it has an impact on SAT. And the more involved I am, the more satisfied I am, and probably the less stressed I will be.
Because, okay, so go ahead and describe that.
Because I'm more involved with my organization, I feel like I have more social support, which allows me to be more satisfied within my group and have ways to deal with stress, which would thereby reduce that.
And also, do you think, in your opinion, is there also a linkage of the organization involvement and stress?
Yeah.
Okay, yeah, can you?
So, the social support that you have through organizational involvement would reduce your stress because you have people to rely on, you have a network of people at work that you can work with and gain support from. So there's a relationship between organizational involvement and stress.
Perfect. Please, let's give both of them a big hand. Excellent. Thank you. Are both of those plausible models? In your opinion, are both Stacy and Zach, you're two, do you think those are both plausible? They are, aren't they? I mean, I think they come up, and you, Stacy, I could probably send you up here, and you might come up with a different one. You might decide that stress is the variable out there, which impacts involvement, which is, right? You may have a very different model. So in other words, here what we can start examining with this type of model is, it's kind of like regression, isn't it? Even the vernacular used was very similar to regression or correlations. But now, you can start getting to a more, it's almost more of a dynamic mode of modeling, where you say, I think involvement does impact stress, but then Chad would say, but you know what though? I think it passes through satisfaction. Which means that satisfaction kind of serves as an intervening variable, or transmitting variable, or what we call a mediating variable. So what we can start doing with these more complex models, which really seem to address human behavior, we can start looking at models exactly like this. Now, this model is simple enough, I can do all this in regression analysis, easily. I can show you how to do path analysis in regression. Easy to do, there's books out there. I've been getting a host of books on this, but I'm going to show you the beauty of doing this in structure equation modeling software. So what we're going to be doing the next couple weeks, you're going to get kind of a high-line version of it. We're not going to be, I would want to spend a whole semester on this. You're going to have enough nuts and bolts where you can test path analysis, and you're going to test a model that has multiple variables. So maybe organization involvement is measured by 3 individual items. Satisfaction, 3 individual items. Stress, 3 items. So this is really going to be called structure equation modeling. And what you're going to be doing initially, everybody, is kind of a psychometric thing called confirmatory factor analysis. Confirmatory factor analysis is the close cousin of EFA, but exploratory, you went ahead and just see what the computer spit out, right? You did your Verimax rotation and extraction, and then the computer spit this out, because it's the unrestricted model. Here with CFA, in other words, I'm saying these 3 items only load on involvement. These 3 only load on satisfaction. These 3 load only on what? Stress. So CFA, you are setting up a postulated, hypothesized model and testing it. So the beauty of path analysis and confirmatory is more control, because you are the one setting up the structure of the model. EFA, you didn't set it up. You just said, here's your 23 items and go at it. Now, a few of you in your homework then constrained it to 2 or 3 or 4 factor solution, of which some of the fit still wasn't that great. And it may or may not make sense. But what's cool about CFA is you can start with your 3-factor model. Then Stacy says, well, you know what though? I think involvement and satisfaction really are 1 factor. She could then test a 2-factor model. And you get all these indices of fit to see which one fits the best. So what you also get by using AMOS, which is the software we will be using, because it's got a license with SPSS and the one available to Alliant, is you're going to first test a path type model with multiple indicators, multiple variables, and you'll be doing CFA. Then, with or without the same constructs, you're going to do a structure equation model exactly as Chad set up here. In other words, you can test if that mediates the involvement-stress relationship. So what's really cool about structure equation modeling, or what we call latent variable modeling, is the ability to really test these multivariate models. Why do I use the term latent variable? Technically speaking, if I had you only do a path analysis with the individual variables, you would have squares as the graphic. Because this is the actual variable. You have 1 item, am I involved in the organization? I am satisfied on the job. I feel stressed on the job, individual items. However, would you say things like involvement, satisfaction, and stress tend to be more complex than what an individual item can do to encompass the full construct validity of the phenomenon you're measuring. You're all taking psychometrics, right? And you've probably had some exposure to construct validity, of which there's myriads evidence of construct validity. And remember, it's not validity of a test or reliability of a test. Remember, the test is not valid or reliable. It's the inference made from the score. And the ARA and APA is taking great pains to make sure people don't say a test is valid, a test is reliable. It is, the validity is the inference made from the test score. That's what's being validated. That's what's being validated, not the instrument. So that being said, everybody, Chad could test this. But Stacy says, you know what though, I have multiple items for my survey. Which means, you see I have circles instead of squares? The circles indicate a latent variable. What the heck is a latent variable? The book you're using for psychometrica, Rakoff and Markulides. George is the editor of structural equation modeling, which I'm on the editorial board and have been for years. And that's a whole journal devoted to latent variable modeling. What is a latent variable? Depression, satisfaction, anxiety, fear. Those are just constructs we've conjured up and somewhat reified them via these individual items. I feel stressed on the job. I feel uptight on the job. I get nervous when I go to work. So hopefully those items are reflective of this thing, this phenomenon called stress. That's a latent variable. That's a latent variable. So that's why sometimes SEM in the early days was also called latent variable modeling. Because we soon found these weird things to test that are complex constructs, that are multidimensional, that are truly the epitome of multivariate stats. And how do we model them simultaneously without going bonkers? The MANOVAs of the world ain't going to cut it. And we found structural equation modeling once the computers caught up with the ideas, right? The ideas have been around for years. Geez, since the 40s and earlier. Even Sewell Wright in the early 20s and so forth was doing path analysis. But once the computers caught up, we could do stuff like this and made much more model. You talked about quadratic. I can add a quadratic variable. I can even add moderators. I can do things like mediated moderators, moderating mediators. I can add a mediator and a moderator. I mean, it gets really complex. I can have multiple groups. Do you think males and females might fit differently? Factor analysis. Is there a chance Westernized instruments for Americans might fit differently than Koreans? All the instruments that we hold dear to maybe don't fit so hot when you test them from CFA, confirmatory factor analysis, and other groups. So the beauty of structural equation modeling is being able to look at these more complex structures, and what you're going to find is you have these indicators, what's called reflective indicators, that map on to these constructs. And how do they map on? It's based on your theory. It's based, you've put in your due diligence, you've done your work, and that's one nice way of actually construct validating your instrument. One way of validating the inferences made from the score is by doing a CFA. EFA is great, and you'll do it for your take-home. But you're also going to do CFA as an assignment because it's a stronger model. It's a stronger model because you're going on a limb saying, you know what? These three items measure this. 3 measure this. EFA has all items loaded on all constructs, right? Has all of them loaded on all of them. So, with that being said, everybody, what I plan to do then, the remaining schedule is next week we will get, we'll pretty much be able to finish everything about path analysis. We'll definitely be able to finish CFA. The 6th, we will be able to probably finish SEM. And the 13th, there's a good chance we'll still be able to do an in-class presentation. I think we're going to be able to be fine on doing it in class. What I would like to do is try to get the lecture in on multi-level modeling, and we'll just...